Hello everyone, welcome to 3DV official YouTube channel. In this tutorial we'll consider overlapping of 3D objects in depth. We will implement the basic augmented reality mechanics using Nuitrack. You can find the finished scene with an extended version of this tutorial in Nuitrack Package. The main idea is to deform the mesh with the overlaid RGB according to the depth frame data. Each pixel of the frame corresponds to one vertex of the mesh with the relevant coordinates. We'll start with an empty scene. Let's create an object that will represent the sensor's coordinate system. Name this object sensor space and make the camera object a child of the sensor space object. Reset the transform parameters of the camera object to change its coordinates to 0. Now add a plane object, make it a child to the camera object, and similarly reset the transform parameters of the object. Then change the mesh field in the mesh filter component by selecting a quad mesh to set the dimension of the object mesh to 1. After that, remove the mesh collider component and move the object a little along the z-axis relative to the camera. Add Nuitrack scripts to the scene and enable the specified modules. Save the scene in AR Nuitrack folder. Now let's create a script for processing of data received from Nuitrack and the scene setting. Name the script AR Nuitrack. All calculations will be performed using the update method. First of all, get a color frame, check it for null, and also make sure that this frame is new. To do this, compare the timestamp property of the current frame and of the previous one saved in the last timestamp variable. Remember to update the last timestamp value with the value of the current frame. Now let's declare the update RGB method. As arguments, it will accept a Nuitrack color frame. Call update RGB in the update method. To display RGB in Unity, you need to transfer data from color frames to texture 2D. If the first frame is received, we need to initialize texture 2D. As arguments, pass the dimensions relevant to the color frame dimensions. Set the RGB24 format. There are 8 bits per channel. Alpha channel is missing. Disable map generation for this texture. For the mesh generator, as well as for convenient access to the parameters of generated mesh, create a mesh generator script and add a field that stores a link to the mesh renderer component. Now let's add a material property that will return the material of mesh renderer component. In the AR Nuitrack script, add a field that stores a link to the mesh generator component. Then, as a link to the material texture, pass the link to the generated texture. The main texture of standard material is called main text. To transfer data from color frame to texture 2D, use the load-draw-texture-data method. It takes int ptr as the first argument. This is a pointer for the data in memory, and the second argument is the number of bytes to read. To transfer the loaded data into GPU memory, call the apply method. Then add the mesh generator component to the plane object and add a link to the mesh renderer. Add the AR Nuitrack component to the sensor space object and specify a link to the mesh generator. Now let's create a standard material and assign it to plane object. Run the scene and make sure that this color frame is displayed on a plane. However, Nuitrack delivers data in BGR instead of RGB. We'll fix this later using a shader. Before generating the mesh, add a visual display of the object boundaries to control the validity of the generated mesh. To do this, we'll use Gizmo's overridden rendering method in the editor. Now, using Gizmo's drawLine method, draw 4 lines to constrain the mesh size. Set each point of the line in local coordinates. To transform them into world coordinates, use the transform point method of the current transform. For a mesh with a size equal to 1 and centered at 0, the coordinates of the angles will be multiples of 0.5. Duplicate the rendering of one line by changing the coordinates of the angles. Go back to the editor and temporarily disable the mesh renderer component to see the control lines. Declare the generate method. As arguments, it will take the width and height of the frame. Next, declare a variable of the mesh type that will store the generated mesh. Create a new mesh and set the index format of uint32. This will allow to use up to 4 billion vertices instead of 65,000 for uint16, which is equivalent to a 256 by 256 pixel image. To get access to the mesh of the current object, add a field with a link to the mesh filter component. Now we can override the current mesh with the generated one. Declare methods for generating UV map points and mesh triangles. Triangles are a list of vertex indices that need to be connected to each other to get a plane. The UV map determines the ratio of vertex coordinates with texture coordinates. As an argument, we pass the frame size. Call these methods in the generate method. After generation, you need to update the normals and boundaries of the mesh. Generate a point for each pixel of the depth frame. For this, we use nested loops. The first loop will go through the rows of frames, the second through the columns. The limits of both loops are greater by 1 than the given values. This is needed to cover the pixels at the image edges. After that, calculate the normalized coordinates of the pixel. Since the loop counters are of an integer type, we convert them to float. Transfer the pixel coordinates to the point coordinates, subtracting 0.5 for each value to align the mesh coordinates with reference to 0. To pass points to the mesh, first fill in an array with the points. Make a list of points. Then add the created point to the list. Now transfer an array with generated points as the vertices for our mesh. The number of points generated is not enough for creating a mesh. It is necessary to set the indices of the vertices that will form the triangles. However, there is a condition for the correct triangle orientation. To make the plane of the triangle visible from the observer's side, the vertices must be pointed clockwise. Otherwise, the triangle will face the opposite direction. This rule applies to each triangle in the mesh. Add an array to store the indices of the triangle vertices. Similarly to the algorithm for generating points, we'll use the nested loops. Please note that the limits of the loop for columns and rows are less by 1 than the actual frame size. This happens as we go around each point in a neighborhood equal to 1. Now for each point, we go around clockwise through adjacent points with a step 1. For each pixel, calculate the index of the generated point that corresponds to its coordinates and sequentially add each such triple of indices to the list of indices for triangles. Actually, each pixel is a rectangle that consists of two triangles. Transfer the list of triangle vertex indexes to the generated mesh. As the second argument, the setTriangles method takes the submesh index. In our case, we transfer 0, since the mesh consists of only one submesh. Then call the generate method of mesh generator in AR Nuitrack script. For the mesh generator, we will specify a link to the mesh filter component. Run the scene and make sure that the generated mesh is correct. Now add the UV map generation. The UV map is the correlation between the three-dimensional coordinates on the object and the texture coordinates. The UV map is represented as a list of two-dimensional normalized vectors. In our case, it is enough to specify two-dimensional coordinates of all vertices. Since the coordinate system along the y-axis for points is directed upward and the texture coordinate system is directed downward, we need to invert the y-axis. Add the generated point to the list. Pass the generated list of UV coordinates to the mesh using the setUVS method. The method takes a texture channel as its first argument. In our case, it equals to 0. Run the scene and make sure that the texture is displayed on the plane. Now add an alignment of the aspect ratio of our plane with the aspect ratio of the frame. Then calculate the aspect ratio for the original frame. If the aspect ratio is greater than 1, that is, the frame looks more like a horizontal rectangle, then we need to adjust the vertical mesh size. Otherwise, adjust the size of the mesh horizontally. Run the scene and check that the mesh aspect ratios are set correctly. Now let's make the generated mesh completely fill the frame. Declare fitMesh into frame method. It will take a color frame as arguments. Let's calculate the aspect ratio of the original frame. Then we'll need to get access to the camera to correctly position the mesh in the frame based on the camera FOV and the screen aspect ratio. Please note that each game object already has a default camera field. To avoid conflicts, add the new modifier. Now let's define the target aspect ratio that we will align the mesh size with. If the original frame is stretched more horizontally than the screen, then we take the aspect ratio of the screen as the target aspect ratio. This happens because in Unity the camera FOV is responsible for the vertical angle of view. When the frame is wider than the screen, we set the mesh size based on the camera FOV, so that its vertical edges match with the vertical edges of the screen. Then let's calculate the vertical angle of view of the camera in radians divided by 2, since we will consider half of the camera pyramid to use a right triangle in the calculations. Now for the mesh we can calculate the scale adjustment value. This value is defined as the product of the camera mesh distance, tangent of the camera's angle of view, and the target aspect ratio. Apply scale adjustment to the x and y axis of the generated mesh. Multiply the value by 2 since it is calculated for a right triangle. Add call of fitMesh into frame method in update RGB method. Add a link to a camera to the AR Nuitrack component. Run the scene and check that the mesh completely fills the frame while maintaining the aspect ratio. Also check this for various screen aspect ratios. Make sure that the mesh correctly maintains its dimensions when approaching or moving away from the camera. Before we start working with depth, go to the Nuitrack config and change the value of depth to color registration to true. Get the depth frame in the update method. Similarly, with the color frame, add a check for null. We will move all processing of the depth frame to the update height map method. It takes a depth frame as arguments. Add a call of the update height map method in the update method. To align the distortion of the object's perspective in Unity with the real image, it is necessary for the camera in Unity to set FOV equal to the FOV of the depth sensor. We can get data on the sensor FOV in the output mode. Since in Unity the camera FOV is specified for the vertical axis, but output supplies the data for the horizontal axis, we should make a transformation. For this, multiply the horizontal angle of view by the inverse aspect ratio, that is, the height of the frame divided by the width. Now apply the calculated angle of view to the camera by converting it from radians to degrees. Run the scene and check the camera angle. To deform the generated mesh, we will use shaders. Shader is a program for GPU. Its advantage is that you can parallelize a lot of simple tasks into many threads. The mesh will be divided into groups, and for each of them, the GPU will allocate a core that will perform calculations simultaneously with the others. Let's consider the shader structure. At the top is given the name and path that we will see in the material editor. They are followed by open properties. Below is a list of subprograms. Frag program returns the color of the current pixel. Vert subprogram returns a structure describing the vertices of the current fragment. Now let's change the color scheme of the image from BGR to RGB by simply changing the channel order. Now go to Material and set AR Nuitrack Unlit as a shader. Run the scene and make sure that the image has the correct color scheme. A depth frame is a set of pixels, where each pixel stores the depth value in millimeters as a single value in U-short data format, which corresponds to U in 16. To put the data in the shader and in the GPU memory on the CPU side, the data is placed in the compute buffer and transferred to the shader. On the GPU side, they are already represented as a structured buffer. Since shader doesn't have int16 support, we will use int32. This will cost one int32 value to store two int16 values. Let's declare a structured buffer in the shader. The buffer value type is uint. Also connect the buffer to GPU global registers. This is useful if you need to get this data from another shader skipping the CPU. Now put data from the CPU into the compute buffer. We just need to initialize the compute buffer once and then record the values into it. When initializing the compute buffer, we indicate the number of elements, half as many as in the original frame, but the size of the element itself will be int32, not int16. This will cause two int16 values to be placed in one int32 cell. Then, for the mesh material, we specify a link to the created buffer. Before using the depth frame data, copy it from memory to a byte array. Initialize a byte array with the same dimension as the dimension of the depth frame data. Then perform data transfer using marshalling. However, this requires adding a directive to the system runtime interop services namespace. Now, using the marshal copy method, copy the data into the byte array. As the first argument, transfer the int ptr pointer to the data. The second argument is a byte array. The third and the fourth arguments are the start index and the data length, respectively. The marshal copy performs fast byte-to-byte copying of data without regard to their type. Now the copied data can be transferred to the compute buffer. In future, to calculate the index of the pixel and the structured buffer, we need to know both the width and the height of the frame. Declare the corresponding variables in the shader. Add the transfer of the width and height of the frame to the shader from the CPU using the setInt method for the material of our mesh. Then calculate the index of the current pixel relative to the depth frame buffer. To do this, it's enough to multiply the frame width by UV Y coordinate and add X coordinate. However, since the UV coordinates are normalized from 0 to 1, we need to multiply the Y coordinate by the frame height and the X coordinate by the frame width. Now we can get the depth value for a pair of pixels in int32 format. Since we're reading two values at a time, the index for depth buffer must be divided by 2. This can be done quickly using the operator of the right shift by one register. Now let's consider the algorithm for how to separate two int16 values recorded in int32. To get the first value, we need to make a shift by 16 bits to the right. To get the second part, first we make a shift by 16 to the left to 0 the first part, and then shift back by 16 to the right. Let's add a transformation to get one value from a depth pair for the current index. Before you start the mesh deformation according to the depth map, you need to know the maximum depth recognized by the sensor. You can get this information on your sensor manufacturer's website. For the sensor used in this tutorial, the value equals to 8 meters. However, you can specify larger values and this won't affect the operation, but only the accuracy of the depth approximation. Pass this parameter to the shader using the setFloat method of our mesh material, and also move the mesh away from the camera at a distance equal to the maximum sensor depth. The idea is that the depth map will be generated by shifting the plane vertices towards the camera. Add the parameter of the maximum sensor depth to the shader. Now we'll get the normalized depth value. For this, divide the depth of the current pixel by the maximum sensor depth. The maximum sensor depth should be multiplied by 1000, as Nuitrack delivers data in millimeters. Since the depth map is built by a reversal, that is by shifting the vertices towards the camera, the depth values are to be inverted. When creating a depth frame on distant objects, we face the formation of shadows from objects located closer. The depth value in such areas is equal to 0. For an inverted depth map, we need to zero these areas. To shift the vertices towards the camera while preserving the distortion, add a variable which stores the camera position. Now let's calculate the direction vector from the current vertex to the camera. The displacement vector for the current vertex is equal to the product of the normalized vector of two camera direction and the depth value for this pixel. To get the new position of the vertex, add to the current position the product of the displacement vector multiplied by the distance between the vertex and the camera. Transfer the new value to the vertex describing structure. Since the shader makes calculations in the mesh local space, the world coordinates of the camera should be converted to local coordinates relative to the mesh. You can do this by using the inverse transform point method used by transforming the mesh object. Transfer the calculated value to the shader by the setVector method. Let's run the scene and make sure that the depth map has been generated. Also make sure that when you change the value of the maximum sensor depth, the map remains correct. To check the overlapping of 3D objects, add a test cube to the scene. Set its size and position as in the real world. Run the scene and make sure that we can go around the cube and overlap it with our body. Now add the alignment of objects to the real floor. Add the update floor method. It will take user frame as arguments. In the update method, add the receipt of the user frame and also check for null. Then call the update floor in the update method. In Unity, it is convenient to represent the floor plane as a plane structure. From the user frame, we can get an arbitrary point on the floor plane, as well as the floor normal. Remember to multiply by 10 to the power minus 3 to convert millimeters to meters. To avoid shaking of objects within the small changes in the floor normal or the height from the floor to the sensor caused by the calculation error, add a floor plane for the current frame, which we will compare with the plane for the previous frame. Initialize the plane structure. As arguments, it takes the floor normal as an arbitrary point on the floor plane. In the case for the first frame, the plane for the previous frame is not initialized. Null checking for structures doesn't work, so you need to check for the default value. If the plane for the previous frame is not specified, update it with the current value. Let's calculate the change in height to the floor at the sensor location point. To do this, we'll project the sensor position onto the floor plane of the current and the previous frames using the closest point on plane method. Since the sensor is the origin of the coordinate system, its coordinates are equal to 0. Now let's add the delta of normal tilt angle change and the delta of change in floor height under the sensor. If the normal deflection angle between adjacent frames is greater than the specified delta, or the change in height at the point under the sensor is greater than the specified height delta, we regenerate the floor plane using the actual values. To align objects with the real floor, analyze the following mechanics. When we tilt the sensor, for example, to the left, looking at the sensor from the front, the image will also be tilted to the left. To compensate for the sensor tilt without replacing the actual tilt of objects on the scene, it is necessary to tilt the camera in the opposite direction, that is to the right. This rule applies to all axes. Now calculate the normal vector reflected from the horizontal plane. This can be done with the vector reflect function. As the first argument, we'll pass the inverted normal vector, and as the second, the normal vector to the horizontal plane, that is the vector up. Only normal is not enough, we need to know the direction of the sensor space. To do this, add a field that will store a link to an object that simulates the sensor space. Take the forward vector as the direction vector. Now we need to align the forward vector at 90 degrees with the normal vector. This can be done using the vector ortho-normalize function. We transfer the normal vector as the first argument and the space direction vector as the second. Note that before the arguments we set the ref modifier. This means that we transfer links to values, not the actual values, since the values themselves will be changed inside the method. The camera orientation can be calculated using the look rotation quaternion. As the first argument, we'll transfer the forward vector, as the second, the reflected normal vector. Now let's change the camera orientation. To make the transformation smoother, use the quaternion lerp function. Transfer the current orientation of the camera as the first argument, and the target as the second. To adjust the transition speed, add the floor correction speed factor. Multiply the delta time of the current frame by the edit factor. The local position of the camera along the y-axis will be equal to the inverted position of the sensor projected onto the floor plane. To make the transition smooth, use the vector lerp function. We transfer the current position of the camera as the first argument and the target position as the second. The time delta of the current frame is also multiplied by the correction speed factor. Add a link to the sensor space object in the AR Nuitrack component. Run the scene and tilt the sensor to make sure that the objects relative to the floor are aligned correctly. Now let's test 3D object overlapping. We hope that this project was useful for your case. If you enjoyed the content of this tutorial, click like and subscribe button so you can receive more content like this. Thank you for your attention, bye!